guys, my name is Kendra Farrell. I'm from the University of Pittsburgh, and I'm here today to talk to you guys about the James Webb Space Telescope. So the James Webb Space Telescope is built by NASA, the European Space Agency, and the Canadian Space Agency as a collaborative effort. So it will be replacing the Hubble telescope. So I'm just going to give you guys a brief little background about the Hubble telescope before we get into the James Webb. So the Hubble telescope views light in the visible spectrum. So that's how it takes these beautiful pictures of all of the stars and nebula that I'm sure you guys have seen. They're pretty common around. It orbits the Earth, and it has a 2.4 meter primary mirror segment, which you can see here. It's pretty small. It's a little bit larger than a person, and it weighs about 1,100 kilograms. So that's pretty heavy, and I'm sure you guys are aware that. I'm sure you guys are aware that it's pretty difficult to launch something into space that's pretty heavy. So that's why the Hubble telescope has to orbit so close to Earth, because it's very heavy. It's very hard to get it out farther than that. The James Webb Space Telescope, on the other hand, views light in the infrared spectrum. So that allows it to get a clearer picture, and I'm going to be telling you guys more about how it does that in the following slides. It also orbits the sun in the L2 zone. So that is the Lagrange point 2 in relation between the Earth, the sun, and the moon. So this point allows the telescope to actually follow the orbit of the sun instead of orbiting the Earth itself. So it's close enough, it's like a Goldilocks zone. It's close enough between it's close enough to the Earth that it's not pulled out to orbit something else, but it's close enough that it's not orbiting the Earth itself. It's this really great zone. And it has a 6.5 meter primary mirror segment, and it's segmented into 18 sections, which you can see here. And it weighs 6,200 kilograms. So this allows it to orbit as far away from Earth as it does. It actually orbits 1 million miles from Earth at this point right here, the Lagrange point 2. So this figure right here represents the distance between the Earth and the sun as compared to these Lagrange points. So there are 4 primary objectives of the James Webb Space Telescope. It will be searching for light from the first stars and galaxies. It will be studying the formation and the evolution of these galaxies and trying to discover life on other planets. So it's capable of detecting the chemical composition of these planets because it views light in the infrared spectrum. And that's going to allow us to see how the universe really formed and came together as a whole. So it's really interesting. So it's done using cryogenic mirrors. So these mirrors are made of beryllium coated with gold. So beryllium is a really lightweight material, and it's very inexpensive. The only problem with it is that it's kind of brittle. So in order for the telescope to function properly, it has to have these mirror segments reflecting. I'm sure you guys are familiar with how a telescope functions. It captures the lights in the mirrors of one segment, reflects them back to a second segment, and then reflects that back to your eye. So these cryogenic mirrors, how much a telescope can see is directly proportional to the size of its mirrors. So because the mirrors are 6.5 meters across in diameter, it allows it to see 7.87 times 10 to the 22nd miles away from its orbital location, which is incredibly far. It's going to allow us to see 13.4 billion light years into the past, and the universe is only 13.7 billion light years old, which will allow us to see these first stars and galaxies really as they form. Why are we using gold? Because gold reflects infrared light. The infrared light allows you to see through the clouds of dust and through these nebula that are so dusty from the pictures of the Hubble telescope. Gold also has a similar coefficient of thermal expansion to beryllium, which allows it to really, if it gets too cold, it's not going to shrink at different rates. And if it gets too hot, it's not going to expand at a different rate than the beryllium. So this allows it to stay really close together. So the infrared light will reveal more information than the Hubble telescope does with the visible spectrum, allowing you to really get a clearer picture and to see these stars and galaxies as they form. The telescope is protected by sun shields, which are displayed here, which diffuse the sunlight so the telescope doesn't get too hot, because it has to function at 39 Kelvin, which is a very, very low temperature, obviously. And this allows it to protect, these sun shields protect the very sensitive materials on the inside of the telescope. how it collects the light is through microshutters, which are a completely new innovation by NASA, which allow it to observe multiple things at the same time. So how this is done is it collects the light through these, like, they're kind of like switches. They open and close to collect light from these objects and from these interstellar nebulas and galaxies and things like that to really allow you to analyze the planets as they form. So the James Webb Space Telescope is a space transformer. It's incredible. It's going to be folded up into an Ariane 5 rocket and launched 1 million miles from Earth, and it's going to unfold on its journey, which is crazy. So unfolding the secondary mirror is going to be a little bit of a challenge. It's a very, I have an animation here. It's a very fragile piece. So here you can see the solar panels, which will be powering the telescope directly. Now it's the unfolding of the sun shields, which protect the telescope from heat from the sun. And then they unfold and they expand and inflate, kind of like a balloon. So this really, it's going to like rotate so that this part isn't ever like affected by the sun. So yeah, this is the primary mirror segment collecting the infrared light, sending it back. The back of this telescope right here has all of the very sensitive materials that are really fragile and really delicate. And this segment right here, this secondary mirror, is the point that they're really nervous about unfolding properly. This is the only part of the telescope that if it doesn't unfold properly, the telescope can't function. So that's what they're worried about testing most. So this telescope is really incredible, beautiful innovation by NASA. Yeah, going to be launched in 2018. Really exciting. Does anyone have any questions? Yes?
How much longer will the Hubble actually last?
The Hubble was launched in 1990, so it's actually still functional, and they don't have any foreseen issues with it remaining functional, so these can function in parallel.
Okay, thanks.
Yeah?
The material you presented, you made something, or whether you got from NASA or?
Oh yeah, I wish that I made this. No, this is an animation from NASA. Yeah. Any other questions? Yeah.
The Hubble telescope is considerably closer to Earth, so it's probably easier to transmit data between the two, but how are they going to do it if it's 1 million miles away? They haven't figured out.
So this satellite right here will be transmitting the data between Earth and the telescope. So this is actually, it actually functions a lot quicker than you'd think. The telescope is going to be in orbit for is going to be functional, they predict, for 10 years. So this will actually be transmitting the data back and forth from Earth.
Do you know that the resolution or kind of like the bit rate? So when it takes an image, how many pixels in that image?
You know, I'm not exactly positive, but yeah, I didn't exactly look into that specifically, but here you can see how much clearer the image is in the infrared spectrum as opposed to the visible spectrum, which the telescope can see. So this is a projected image of what sort of pictures the telescope will be able to take as it's orbiting.
Okay, great, thanks.
Yeah?
Is there any reason why NASA take the L2, not the L5?
Yeah, of course. So the L2 zone is really just that sweet spot so the telescope can orbit the sun. So how this works is the telescope is going to be, so as the Earth orbits the sun, it's rotating and the moon is orbiting. So at this critical point here, it's far enough away from Earth that it can see as far as necessary. And it will also be able to maintain the orbit around the sun. So it doesn't get pulled into the orbit of the sun, and it doesn't get pulled into the orbit of the Earth to really prevent that. Does that make sense?
Is something on the launch point?
Yeah, it's the right.
I think there is another reason could be, a solar particle actually not directly hit the telescope. Otherwise, there's many of disturbers during the communication.
Yeah,
it's kind of like in the shadow of the Earth, right?
Yeah, exactly, and that's another function of the sun shields as well, to really prevent any remaining fragments from affecting the telescope negatively.
Anyone else?